In section 3.2, we're going to talk about polynomial functions and their graphs. But the first thing that I want to do is I want to establish some vocabulary. If you have a polynomial, such as 3x to the fifth plus 6x to the fourth minus 2x to the third plus x squared plus 7x minus 6, we're going to call the monomial at the beginning the leading term, where 3 here is my leading coefficient. The leading coefficient is always going to be the coefficient in front of the monomial in the polynomial with the largest exponent, no matter what order it's written in. However, we tend to prefer that our polynomials be written in descending order of powers. So we would say that this is a degree 5 polynomial. Now inside of this polynomial, remember that the term that doesn't have a variable with it is known as the constant. So this one, because it's got an x to the first power, we call that the linear term. So x squared would be the quadratic term, and negative 2x to the third would be the cubic term, and so on. For polynomial functions, ones that are degree 0, because they're constant, there are just horizontal lines. And polynomials of degree 1 are usually lines that have some sort of angle to them. Degree 2 polynomials, those are parabolas, whether they open up or down. Degree 3 polynomials often have this shape to it. Degree 4 polynomials sometimes look like m's or w's, can also look like quadratic equations. But the thing with polynomial functions is that all the graphs are something called continuous. That means that there is no break in the graph. In Algebra 2, we learned about something called holes. When a graph had a hole in it, that means that there was a point where the graph did not exist. That was discontinuous. Or sometimes we had some graphs that had jumps in them, like part of the graph was here and then the other part of the graph was here. Graphs with jumps in them were discontinuous. A lot of piecewise functions have jumps in the graph. Not all of them, but a lot of them do, and are often discontinuous. So we're going to talk about here polynomials which are continuous. The first thing we're going to do is we're going to look at transformations and monomials. Monomials are going to be the ones that are the graph of y equals x to the nth power. So one of the things we know about cubic functions is cubic functions either look like this or they look like this. They either have little bumps in the middle or they don't. The monomial x to the third looks like this graph, and it passes through the origin. So if the graph has a negative in front of it, it's going to reflect it over the x-axis. So the actual graph of this, if I were to look at it on the coordinate plane, it goes through 0, 0, 1, negative 1, and then the next one is 2, negative 8, so it'd be down here somewhere. And it goes through negative 1, 1, and it goes through negative 2, 8, wherever that is. So the graph of negative x to the third would look like this. Polynomials that have x to the fifth look kind of like cubic functions, except they have a little more lengthy flattened section in the middle of the graph. If you'd like to see what it looks like, just graph it on your calculator. So this particular polynomial would be this graph that's been shifted 1 unit to the left. Remember our transformations from the last chapter. So to look at this graph on the coordinate plane, it would probably look something like this. The graph of x squared, which is just a parabola, this particular transformation would be 3 up. This would stretch it vertically, in other words, it would make it narrower. And this would reflect over the x-axis. So if I look at a basic sketch of this graph, let's see, 1, 2, 3, and it would be narrower, and it would be reflected. So it would look something like this. End behavior is a description of what happens to the y values on a graph as the x values go in the positive or negative direction. We touched on this a little bit in Algebra 2. The way it works is the left side of the graph is the side where the x values are getting more and more negative, and they go in the negative direction forever. Well, if the x values are getting more and more negative on the left side of the graph, on this particular parabola, I want you to notice that the y values, they're going up. And up is the positive y direction. So we say the end behavior is, as x approaches negative infinity, y approaches positive infinity. In the positive, let me write x direction. This is the side of the graph where the x values are getting more and more positive. This graph, again, is going up, so the y values are getting more and more positive. So we say as x approaches positive infinity, y approaches positive infinity. Not all graphs look like that. Here's your general run-of-the-mill cubic function. On this graph, I would say as x gets more and more positive, y gets more and more positive. But in this direction, this is the side of the graph where the x values are getting more and more negative. And the graph of this particular function is going down, which is the negative direction. I could make the graph look like this. It doesn't matter how complicated I make the graph look. The way the end behavior works is this is the side where the x values are positive, because this is the positive x-axis. But what's happening to the graph? The graph is going down forever. And then over here is the side of the graph where the x values are getting negative, but in this graph it's going up forever. So we say for the end behavior, as x approaches negative infinity, y approaches positive infinity. On the right-hand side of the graph, as x approaches positive infinity, x approaches negative infinity. So we want to determine the end behavior of the polynomial function f of x equals negative x cubed plus 20x squared plus 60x plus 2. Now, I don't even need to see what the graph looks like on the graphing calculator. If you want to graph it on the graphing calculator, you can. I just know that because the biggest exponent is 3, and because the leading coefficient is negative, that the graph is going to look something like this. So if you graph it on your calculator, you get something of that general shape. Well, I know that this is the side of the graph where the x values are getting positive, because it's always on the right side of the graph. And the y values are getting negative. This is the side of the graph where the x values are on the negative side. And the y values, well, they're going up, so they're becoming more and more positive. So we say the end behavior is, as x approaches negative infinity, y approaches positive infinity. And on the other side of the graph, as x approaches positive infinity, y approaches negative infinity. I can do this again for this particular polynomial. Y is equal to 8x cubed minus 7x squared plus 3x plus 7. I know because it's a cubic function, and because the leading coefficient is positive, that the graph looks like this. And again, you can graph it in your calculator, but you don't need to if you know what the general shape should be, because I know as x gets more and more positive, y gets more and more positive. As x gets more and more negative, y gets more and more negative. Let's say that I were to destroy all the calculators in the world, but I still gave you a polynomial function and I wanted to know what the graph looked like, sort of in general, nothing extravagant. If I know the zeros of the polynomial function, I can figure out where the graph is above or below the x-axis. Now for this particular polynomial function, the zeros are at 1, -2, and 3. How do I know that? Because I perform the zero product property on this polynomial. Alright, now the next thing I want to talk about is this 0 here, because I want you to notice that on the parentheses it said x minus 3 to the second power. This is known as a double root, or a 0 of multiplicity 2. And when you have a 0 of multiplicity 2, the graph is going to look quadratic at that 0. That means it's going to go to that 0 and it's going to bounce off the x-axis rather than pass through like most graphs do at a 0. So I'm going to make myself a little number line with these particular zeros. So one of my zeros is at -2, one of them is at 1, and one of them is at 3. And I'm going to find out if the graph is positive or negative at in between these zeros. So let's start with this region over here that's to the left of -2. How do I figure out if it's above or below the x-axis? Well, how about I test a value? I'm going to plug in -3 and I'm going to see what happens. So I'm going to do -3 minus 1 times -3 plus 2 times -3 minus 3 squared. So that's -4 times -1 times -6 squared. This is a positive. These two are positive, and so positive times a positive is a positive. That means over here the graph is above the x-axis. And notice that I didn't even do all the work. I just did some of the work to figure out if it was positive or negative. Now I'm going to go back and I'm going to look at this region here between -2 and 0 and 1. Is that part of the graph above or below? The easiest thing to try out is 0. So I'm going to plug 0 in. 0 minus 1, 0 plus 2, and 0 minus 3 squared. So I've got a -1 times a 2 times, this is going to be 9, and a negative times a positive is a negative. So I know that the graph between -2 and 1 is below the x-axis. Now I'm going to test between 1 and 3. So now I'm going to go try 2 to find out what happens here. Alright, so I've got 2 minus 1, 2 plus 2, and 2 minus 3 squared. So this is going to be a positive, this is going to be a positive, this is going to be a positive, so it's a positive. So this part of the graph is above the x-axis. And then I'm going to do this one more time, and I'm going to check out what happens over to the right. So when x is bigger than 3, so how about I try 4 and find out what happens. Positive, positive, positive. Oh, that makes sense because I said that what's going to happen is when I go graph this, the graph is going to look like this. Remember I said this is called a double root, or a 0 multiplicity 2, and the graph's just going to bounce off there. So it makes sense that on either side of that 0, the graph is above the x-axis. So even though that's not a perfect graph, it actually gives me kind of a sense of what's going on. And that's